All right, so what are we going to be studying today? Induction, right? Because we studied induction the first day, we studied induction the second day, therefore by induction we are studying. All right, but we will be doing induction with the arithmetic mean, geometric mean inequality. So out of curiosity, how many of you have seen the AM-GM inequality before? All right, this is one of the staples in problem solving. It's an extremely useful inequality, and we will see some of the applications today as time permits. There are lots of different proofs of the arithmetic mean, geometric mean inequality. I will give you a TlQ proof just because this is a good way to review things from TlQ, which may or may not be crystal clear in your memories. I will do the standard boring inductive proof. I will do the strange backwards jumping induction proof. I don't know if any of you have ever seen an inductive proof like this, where you overshoot what you want and then you fall backwards to get. It's a really nice proof. And then we'll talk about maybe some applications, both in terms of contest problems and, if time permits, in terms of research. So 2 summers ago, I actually had a small student working with me on a problem related to applications of generalizations of the arithmetic mean, geometric mean inequality, and continued fractions. All right, so first, we should probably state the arithmetic mean, geometric mean inequality. So the arithmetic mean is going to be a1 plus an over n. The geometric mean is the product a1, an, and then take the nth root. Or if you prefer, a1, an to the 1 over n. So when you talk about the average of a number, or a set of numbers, there's different meanings. Typically, which one do we mean, the arithmetic mean or the geometric mean? Arithmetic, right? When you talk about the average height, the average score on an exam, the average temperature in the year, you typically mean the arithmetic mean, right? Anybody see any way to connect the two? Yes?
If you raise the arithmetic mean, you might get the geometric mean in some term.
Okay. So if you definitely raise this to a power, if you raise it to the nth power, you will get one of the terms coming in. You'll get a lot of other stuff as well. So you're on the right track, and there are inequalities related to that. Any relation between an arithmetic mean and a geometric mean, it may not be with the same set of numbers, but can you relate a geometric mean to an associated arithmetic mean? Yes?
If all the terms are the same, then they're equal.
Okay, so if they're all the same, they're equal. Okay, so there's a special case, the AM equals the GM if all the terms are the same.
Maybe take the logarithm.
Excellent.
Geometric mean, you get something that looks like the arithmetic.
So if I take the logarithm of this, I get an arithmetic mean. So the log of the geometric mean is the arithmetic mean of the log. You know, this is shorthand for the log of a1, an to the 1 over n is the log of a1 plus the log of an over n. Whenever you see products, you should always be thinking logarithms. It's extremely useful. It's a very good advantage to get into. So whenever you see a logarithm in this class, just say logarithm. You'll be right at least 80% of the time. Okay? So now the question is, what relationship do we expect to have between the arithmetic mean and the geometric mean, and what kind of conditions do we want to have on these numbers? So again, whenever you see quantities, whenever you see statements, you want to ask yourself, all right, for what values am I going to be studying this? So any thoughts about what we should assume about the A's? Yes?
They're either entirely positive or there's an even number of odds.
Okay, so if some of the A's are negative, we now have a danger of having the square root of a negative number. And then in terms of comparing, that's going to be horrible. So we will assume the AIs are greater than or equal to 0. If any of the AIs equals 0, is the problem interesting? No. So often we might even just assume the AIs are greater than 0. Because if one of the A's is 0, the geometric mean is 0, the arithmetic mean will be larger, unless everything is 0. So we have equality if AI is always AJ. And it turns out This is the only time we have equality. So the only time the arithmetic mean and the geometric mean are equal is when all the numbers are equal. And then in that case, it doesn't really matter. They both measure the same thing. So the question is, which do you think is going to be larger, the arithmetic mean or the geometric mean? Yes.
Arithmetic.
Okay, why? You're right, but why?
Because if it were 0, then the arithmetic would be bigger.
Good, if one of these a's is 0, the arithmetic mean will beat it. So what I can do is I can send one of the a's down to 0, and that's going to decrease the product. And if I send one of the a's down to 0, another one of the a's goes up. So we believe, at least in some regions, the geometric mean will beat the arithmetic mean. Okay, so the intuition, the arithmetic mean will beat the geometric mean. The arithmetic mean should be greater than or equal to the geometric mean. This is not a proof, nor does this actually show that the arithmetic mean is always greater than or equal to the geometric mean. Maybe there's some really bad choices where the geometric mean beats the arithmetic mean. It turns out that's not the case. It turns out the fundamental inequality is this is true. So, is true. All right. So this is a statement about non-negative numbers, and we have n of them. What value n should we look at first? 1, right? You know, build up your intuition, start off with a simple case. Is it even worth writing on the board? No. All right. So n equals 1 is trivial. N equals 2 is interesting. And in fact, n equals 2 uses the most important inequality of all mathematics. And yes, I'm saying that in the course of discussing another inequality in mathematics. So x squared is greater than or equals 0 if x is complex, or x squared is greater than or equals 0 if x is real. This is one of the most useful inequalities in all mathematics. So essentially, whatever you have, if it's real, if you square it, it's not negative. It's amazing how many things this leads to. So over here, if we look at the square root of a1 minus the square root of a2, what do you know about its square? It's not negative, right? So it's greater than or equal to 0. So now if we multiply things out, we get a1 plus a2 minus 2 square roots of a1, a2 is greater than or equal to 0. If I bring this over to the other side and I divide by 2, I get a1 plus a2 over 2 is the square root of a1, a2, or if I want to write it in a really pedantic manner, a1, a2 to the 1/2. Yes?
What's that first line? The square, yeah, where did that come from?
It came from the most important inequality in all mathematics.
So what's our x?
What would you think x would be here? It would be square root of a1 minus square root of a2.
I was like, I'm really confused. Where's that coming from?
This holds for all real values of x. This is one of the most important.
But is there a connection between that AM and GM, or is that just?
Well, this is proving the AM/GM in the case when n equals 2. So if I take a clever choice of x, if I take x to be square root of a1 minus square root of a2, and I square it, when the dust settles after I do some algebra, I get a1 plus a2 over 2, is greater than or equal to, square root of a1, a2. So I get the arithmetic mean is greater than or equal to the geometric mean when I have two objects. So a lot of these math proofs, it comes down to, do you have a clever choice in these problems? What do you want to apply things to? This inequality is always true. When is it useful? Well, if I take x to be square root of a1 minus square root of a2, I get something useful. Okay, so this proves the n equals 2 version. Okay, what's next? N plus 1. So now you assume it holds for n, prove it holds for n plus 1. So we could do this by induction. There's another proof, another geometric proof of the n equals 2 case, which is in the notes, which we look at a circle where the radius of the circle is a1 plus a2 over 2, and you get that as a hypotenuse, and then you get the geometric mean as an altitude. And then just from geometric grounds, it has to work. Right. I'm not going to go through that proof. If you want, read the notes. It will go through that. Let's do the proof by induction now. All right, so everybody comfortable with the case n equals 2? Everybody's happy with n equals 2? All right, so now we want to prove the general case. Before proving the general case, I want to do a little prep work. It may or may not be useful. So prep work. Somebody give me a logarithm you've seen. Anybody seen any logarithms anywhere?
What kind of logarithm?
Give me a log. What's a log you've seen in a math class?
Log base 2.
Log base 2. Okay, so if you're a computer scientist, you see log base 2. If you're a pure mathematician, you see log base. Yes. There's an even more important logarithm. It's the W logarithm. How many of you have seen this logarithm? Anybody seen this one before? No one has seen this? No one? Have you seen this?
Without loss.
Without loss of generality. Right? Without loss of generality. This is the most important. The expanded version is I am too damn lazy to write through all the cases, so I will just do this case and wave my hands and argue that all the other cases follow similarly. Please believe me. Okay, it's a really nice abbreviation. One of my friends in college was not American, and he accidentally said without loss of generosity, which we always found very interesting as to how you would do arguments with or without generosity. But for something like this, are you allowed to just assume things about numbers? No. As an aside, when I was at Princeton many years ago as a grad student, I was doing a linear algebra class, and they had to prove that if Q is an orthogonal matrix, then Q orthogonal implies Q cubed is orthogonal. And orthogonal means O times O transpose is the identity matrix. And this was the proof they gave. Let Q equal I, then Q cubed is I cubed is I, and I transpose equals I. Is this an acceptable proof? No, and as a Yale man, I have no problem, displaying this, proof from Princeton, right? Can you just assume without loss of generality that your orthogonal matrix is the identity? No. Okay? You've got to be very careful. You have to justify and defend whenever you make assumptions like this. This does not belong on the board. This is garbage. This should be gone. Okay? One of the advantages of the eraser. Let's think about what kind of generalizations we can do. When I look at this, I have two different things that I can play with. I can play with the product. I can play with the sum. And again, one of the reasons I'm trying to beat this to death, or I guess there's two reasons. One is I have to fill 50 minutes today. And this is a great way to stretch. But the other is I want to emphasize techniques. I want to emphasize how should you look at problems. All right? This is a technique that's very useful. What would you like to assume about the sum of the A's or the product of the A's? What would be nice? Yes?
If they're both equal to 1.
That would be wonderful if they're both equal to 1. They'd be getting your fuel-efficient sports car. Right? We're not in general going to be able to do that.
Impossible. So they're both equal to 1.
In general, it is very hard for them to both be equal to 1. Okay? So we lower our expectations. So instead of having both of them equal to 1, what can we do? One of them. So can we adjust things so that one of them is true? So if you let bi equal alpha times ai, then the arithmetic mean of the b's, how does that relate to the arithmetic mean of the a's? It's alpha times the arithmetic mean of the a's. What about the geometric mean of the b's? So now I multiply by alpha n times. I have an alpha to the n. I take the nth root. What's alpha to the n to the 1 over n? Alpha. So it's alpha times the geometric mean of the a's. So if I have the inequality that the arithmetic mean is greater than or equal to the geometric mean, holds for the a's, it holds for the b's, and vice versa. This is a wonderful simplification. I can rescale all of my numbers by alpha. So I can choose alpha such that 1, a1 plus an equals 1, or a1 times an equals 1. I can always make that simplification if I want. Okay? Which do you think is going to be easier? Forcing the sum to be 1 or forcing the product?
More useful is the product.
I think it's more useful to have the product because, the sum, I'm not so bad with sums. Products scare me a little bit. And I think the complexity goes down because you have so many terms coming together with the product. I'd much rather set the product equal to 1 than the sum. Okay? So again, right now this is just preliminary legwork. But this is a wonderful principle in mathematics. Is when you're asked to prove something, when you're asked to investigate something, is it sufficient to restrict to a certain case? And say, if I can understand this case, I can understand the general case. Any physicists here, any physics majors? No one? Anybody taking a lot of physics classes? All right. They have in physics what's called the rationalized metric system, where you adjust things so that the speed of light is 1, and the gravitational constant is 1, and I think Planck's bar is 1. And you choose your units so that all these quantities equal 1. And it really removes a lot of the clutter in your equations. They look a lot cleaner. And as a mathematician, I really like that. It puts a lot of things on the same ground. As somebody who has a degree in physics, I admit I have a lot more difficulty looking at these normalized equations because I can't just now look down and see where the physics is because it gets hidden. You have to be careful sometimes about doing too much cleverness and removing too many things. It's nice to be able to glance down and see what's going on. By doing these assumptions, we're going to be able to remove a lot of the terms in the algebra. Okay, so let's continue. Let's do the proof now. So proof that arithmetic mean is greater than or equal to geometric mean by induction. All right, so we've already assumed we've done the base case n equals 1, and we've done the case n equals 2. So now we assume, just so I use the same notation in my notes, assume true for n minus 1 objects, show true for n objects. And what I can do now is I can assume that the product of my n terms is equal to 1. So assume a1, a2, dot, 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 an equals 1. Now I can use the arithmetic mean, geometric mean on n minus 1 objects. I have n objects. I have too many objects. What can I do to cut down on the number of objects I have? So I have a product here with n objects. I can group it in a certain way so I no longer have n objects. What could I do so that I have fewer than n objects?
You just combine two terms.
I can combine two terms. So view as a1 times a2, a3, an equals 1. So if I view it like this, I now have n minus 1 objects. And now I can use inductive step. Now inductive step is available. Okay? This is the hardest part of the proof. This is the hardest part of induction. If you've only seen induction in standard cookbook calculus classes, you will be very misinformed about what induction looks like in the field. Right? In the field, you're not going to have sums of powers and stuff like this all the time. You're often going to have to do some work to see how do I use the inductive step. And the difficulty here is I know something about n minus 1 objects. So I have to somehow combine things in such a way. The easiest thing to do is to combine two of them. Okay? So now we know things about two objects. So we now know a1, a2 plus a3 plus an. And what do I get to divide by? So what do I get to divide by? N minus 1. That's going to be greater than or equal to a1, a2, a3, an to what power? And what does this equal? It's equal to 1. Now you can see really why we want to make that simplification that the product equals 1. You can see how much nicer this is going to make life. So we can multiply through, and this tells us that a1 times a2 plus a3 plus an is greater than or equal to n minus 1. This is damn close to what we wanted. All we wanted was to have these added and not multiplied. And we don't want the minus 1. So we want a1 plus a2 plus a3 plus an is greater than or equal to n. So it would be true if a1 plus a2, so let's look at what's going on. If that is greater than or equal to a1, a2 plus 1. Because if I move this negative 1 over here, I have a1 plus a2 plus 1 is greater than or equal to n. If this is greater than a1 plus a2 plus 1, then my desired inequality holds. So I need a1 plus a2 minus a1, a2 minus 1 to be greater than or equal to 0. Okay? Any questions as to how we got here? All right, so now we're almost done. We've made some simplifications. We've assumed the product of the a's is equal to 1. Do I know anything about a1 and a2? What would be the simplest possibility for us? Let's try to get a sense of, do we think this is true? What would be the simplest possibility for us for a1 and a2? They're both 1. So we need a1 plus a2 minus a1, a2 minus 1 to be greater than or equal to 0. If both are 1, we're OK. We get 1 plus 1 minus 1 squared, which is greater than or equal to 0. So we at least have hope.
Minus 1, minus 1.
Probably. Minus 1 squared, minus 1. Fortunately, we had enough wiggle room that we was fine even with that. All right, so now we have a new inequality in 2 variables. And if we could just prove this inequality, then we would get the arithmetic mean, geometric mean. So we reduced ourselves to a simpler case. Now, the problem is, what if a1 and a2 are both small? Do you think this will be true if a1 and a2 are small? So imagine a1 is 1/5, a2 is 1/5. Would this be true in that case? No. So fails if a1 equals a2. We can even do 1/2. All right. Does this mean the arithmetic mean, geometric mean is false? Why doesn't that mean it's false? Because we've just shown that this inequality does not hold for such cases. It's not a necessary condition. So if we go back over here, come on, camera, there we go. If we go back over here, we have this. We want this. This follows from this one if a1 plus a2 is greater than or equal to a1 times a2 plus 1. But we could still have this greater than or equal to n even if this fails, if the rest of this sum is sufficiently large. Right? If this sum is enormous, we'll be fine. So the problem is, this does not have to hold. If it holds, we win, but we could still win if it doesn't hold. So now things are getting really complex. So in the write-up, I have the write-up as the way you always write up math proofs. You write up math proofs where you throw away all the meanderings, all the wanderings, and you write things up very cleanly, going through step by step by step by step by step. I am deliberately not proving this well. Okay? I'm trying to do a bad job. I hope I'm succeeding. I want to try to give you a sense of the thought process. How would you make these assumptions? How would you attack these problems? How would you go about it? Well, it's good to group them together here. That's nice grouping them together. It's nice to try to get this inequality, but this inequality might not always hold. But I have some freedom in how I assign values to the a's. What do we know about the product of the a's? Product has to be 1. So if both a1 and a2 are small, what else do you know? Some of the other terms have to be big. So maybe what I want to do is have one of the a's large, maybe a1 is large, and maybe a2 is small. And I hope this gives you an idea of why you want to do something like this. So if they all equal 1, we're fine. So maybe consider a1 greater than 1, a2 less than 1. If doesn't happen, we're done. So if you want to write this out really carefully, case 1, all the a's equal to 1. And then this would be case 2. Not all the a's are equal to 1. If not all the a's are equal to 1, one of the a's must exceed 1, one of the a's must be less than 1, because the product is 1. Let a1 be one of the numbers that's greater than 1. Let a2 be one of the numbers that's less than 1. You can see how much we are milking from the fact that the product of the a's equals 1. This idea of standardization, this idea of normalization, bless you, is extremely powerful. So now, note the following. a1 plus a2 minus a1, a2 minus 1 is a1 minus 1 times 1 minus a2. And if I multiply this out, I get a1 plus a2 minus 1 minus a1, a2. Algebra is useful. All right? This is the hard step of the proof. What do we know about this product? So we know a1 is greater than 1. We know a2 is less than 1 and positive. It's more than 0. Right? This is greater than 0. This is greater than 0. The product of things greater than 0 is greater than 0. And that finishes the proof. So the more algebra you know, the easier time you're going to have in something like this. My main physics mentor when I was an undergraduate, Frank Firk, was from England. When he went to school many decades ago, they drilled the students and they knew trigonometric identities up to cosine and sine of 10 theta. And he could just look at the stuff and he could just see. And that was extremely useful for him in his career as a nuclear physicist in seeing how things combined and simplified. This idea of how do you view the algebra is extremely important. It's not easy. The more times you do it, the more you start to recognize patterns. Okay? And so this will be a big part of the course is pattern detection. Okay. So any questions about this proof? Yes?
Again, how, when the case fails, like,
Uh-huh.
how does that, like, not affect, like, proving?
Well, so everything up on the other board was fine, and now we need this to be true. And we have some freedom in terms of what we call A1 and what we call A2. So one possibility is if all the A's are equal, well, the only way they can all be equal and have the product be 1 is this. If they're not all equal, then let's make A1 be one of the numbers that's greater than 1 and A2 one of the numbers that's less than 1.
Is it possible for, like, A1, A2 to both be smaller than 1?
It is, but I'm not going to choose them that way. I have my freedom in what I call A1 and A2. I have a product of n numbers, and I can choose which one do I want to call A1, which one do I want to call A2. Maybe in the original ordering, maybe A1 is greater than 1, A2 is greater than 1, and A3 is the first one that's less than 1. So I relabel, and I shift the order, and I now move A3 to be the second term. Does it matter the order in which I write the terms? No. If I write the terms in a different order, it doesn't affect the arithmetic mean. It doesn't affect the geometric mean. So the key idea here is because order doesn't matter, I might as well arrange it so that I have A1 is greater than 1 and A2 is less than 1. And by doing that simplification, it's going to make the analysis significantly easier. Yes?
To clarify, would you use that final inequality, the fact that it's 0 if and only if either one of those is 1, to prove you have equality, if and only if all
that's
are equal?
That's a good question. Because the next part of the arithmetic mean, geometric mean is you have equality only if they're all equal. Outstanding. I think you can probably do that from here. We've got to be careful because this is going back into, this was used here.
With a much more sophisticated inductive statement.
Right. And so clearly if they're not equal, then they're not going to be equal. So at this point, as soon as I have one of the A1s that's greater than 1, one of the A's that's less than 1, they can't be equal. And then, of course, if they're all equal, so then I think that will give me that the only way that they can be equal is if they're all the same. So yes, that's a good observation. Thank you. Yes?
So I mean, just to understand this, I guess on a higher level.
Yep.
So we assume that all the product of all A1 through AN is equal to 1.
Correct.
And given that we assume that, we can always find an arbitrary sort of like labeling of those n elements such that that equality holds. Right?
Correct.
Equality holds.
Correct.
Because of that, we can-
Correct. And so the whole point is, once we have the product is equal to 1, either all the A's are identical, in which case we're done, or if the A's are not identical, one has to be larger, one has to be smaller. Think of it as you're driving your car, your average speed is 65 miles per hour. Either you were constantly driving at 65 miles per hour, or at some point you were speeding. And at some point you were greater than 65, and at some point you were also below 65. And you can try to argue with the policeman, no, but on average I was traveling the speed limit. Okay. Any questions on this? All right, so before doing another proof of this, let's do an application. All right, how many of you have heard of Heron's formula or Heron's formula? All right, so this is a great formula for the area of a triangle. So I will assume we know this. Okay, so application, area of a triangle. So Heron, or Heron, says the area is equal to the square root of s times s minus a, s minus b, s minus c, and then do I divide by 2? I should probably read this. I think this is the formula for the area of a triangle. Somebody will have to check that later. Where S is the semi-perimeter, which is equal to A plus B plus C over 2. So I can't remember right now if we divide by 2 in Heron's formula, because for what we're doing, it actually doesn't really matter, right? So what am I doing right now?
Divide by 2.
You do divide by 2?
No, you don't.
You don't? Okay. All right. So if we don't divide by 2, it doesn't really matter. All right, so just the square root of this. Okay, so here's Heron's formula. I will assume that this formula is true. What do you think a reasonable question I might want to ask about triangles? So I'm looking at all the triangles with a given perimeter or given semi-perimeter. What's a natural question to ask? So I'm looking at all triangles whose perimeter is 20. What might I want to know? Yes?
Like, which one has the largest area?
Yeah, which one has the largest area? In calculus, you might have done the Farmer-Brown problem, where Farmer-Brown loves rectangles and will not consider any other kind of pen for his cattle other than rectangles, right? And if he has 20 meters of fence, what's the largest pen he can build? And then he has a brother, Farmer Bob, who lives by a river, and he only needs to do 3 sides. What's the best farm? Okay, this is their cousin. All right, and this cousin loves triangles and wants to know what is the maximum area that can be enclosed using a triangle. What do you think the answer is? Equilateral. Okay, and so we could try to figure out, well, what is the best we can do here? I hate using s as a variable. Why is s a horrible variable to use? I'm sorry? Yeah, it looks a lot like a 5, especially the way I write. All right? So I claim that this should somehow be doable using the arithmetic mean, geometric mean. So the claim is 1, maximum area is at equilateral triangle. And 2, the arithmetic mean, geometric mean is useful. All right? Well, if it's an equilateral triangle, then A equals B equals C. Right? And in fact, if I fix the perimeter, do I have to worry about the first square root of s? No, because that's a constant. So I can either include it or not include it. It doesn't really matter. Do you think we should include it or not include it? I've deliberately not thought about how to solve this problem, so I don't know. Do you think we should include that extra square root of s or not? I would say not, because if we don't include it, all the terms are the same. Right? If I do include it, the terms will be different in the special case when A equals B equals C. So suffices, no, sorry, that's a horrible word to use. That's a literary word. Well, log, study the square root of s minus A, s minus B, s minus C. And in fact, if I don't want to study the square root of this, what could I study? I could study the cube root of this, so I want. I could study the cube root of s minus A, s minus B, s minus C. Right? Does it really matter if I maximize the square root or if I maximize the cube root? No. If I care about the value, does it matter? Yes, they'll have different values, but they'll have the same locations of the maximum and the minimum. Why might it be better to use a cube root than a square root? So somebody has to say what you're thinking. They're all the same. What else? It's a product of 3 things. If I'm thinking arithmetic mean, geometric mean, the geometric mean of 3 things involves the cube root. So I really want to look at a cube root of this quantity, not a square root of this quantity. So again, this is 2 different algebraic simplifications. I don't know if this is the right way to do this problem. This is a very interesting class to prepare where I'm deliberately trying not to prepare so that you can get a sense of the thought process. So that might mean we go down a wrong avenue, which is fine. And I don't mind you looking like a fool and being recorded, and you can show all the other people, look at it, and Miller spent 15 minutes doing the following. But I want to show you how you might try to approach something like this, how you might try to use it. So now, if we apply the arithmetic mean, geometric mean, we get s minus A plus s minus B plus s minus C divided by 3 is greater than or equal to the cube root of s minus A, s minus B, s minus C. What is the right-hand side? What is the left-hand side equal? Yes, it's just 2/3 s is greater than or equal to the cube root of s minus A, s minus B, s minus C. And notice this is independent of the triangle. And we have equality if and only if s minus A equals s minus B equals s minus C, i.e. if A equals B equals C, i.e. if equilateral. And here's a nice proof that the equilateral triangle has the largest area for a given perimeter. If I choose anything else, I'm going to have a less than. Right? So I now need to use the full strength of the arithmetic mean, geometric mean. It's not just that it's greater than or equal to, that it's strictly greater than if they're not all equal. And that's the proof. OK, good. It all worked out. Why was this a useful thing to do? We just arranged the algebra in such a way to make it a little bit more amenable to the arithmetic mean, geometric mean. Okay? And again, I had some asymmetries. I had an S and an S minus A, S minus B, S minus C. I want all the terms to look the same. Well, S is constant. It doesn't really belong there. And instead of minimizing or maximizing area, I could do area squared, or area to the 2/3. Okay, so there's a lot of great ideas in approaching this problem. Question?
This doesn't really affect your conclusion, but it's actually 1/3 S.
That's 1/3 S?
I think so.
Oh, because S is the semi-perimeter. Oh, that's right. S is the semi-perimeter. So it's A plus B plus C over 2. So we get 3S, which is A plus B plus C minus 2S is just S. So yes. Fortunately, it is an error that doesn't matter, but yes, it's better to have this fixed. So now I will give OIT the challenge of going back and editing this video and fixing all of that stuff. Okay? It's just a couple of pixels. All right. Any other questions or comments? All right, so what I want to do is, based on the fact that we have 5 minutes, I may skip the backwards induction for now, and I just want to go and do the Calculus 3 approach. Because a lot of you have probably taken a calculus class where you've done a lot of things in multi without really seeing why you care about it, and this is a very good approach. So Calc 3 proof of arithmetic mean, geometric mean. Any econ majors or potential econ majors? Okay, so Lagrange multipliers is extremely important in economics. Hopefully this was covered in your Calc 3 class. If not, let me know and I will send you some handouts on this. So let's let f of a1 through an be a1. So just make sure I want to do it in the right way. OK, I'll do it this way. Is a1 times a2 times an to the 1 over n. G of a1 an be a1 plus an over n minus c. So what I'm doing is I'm saying I want to look at a choice of a tuple of a1 through an such that the arithmetic mean has a given value. Maybe I normalize things so the arithmetic mean has value 1. I don't really care right now. This is my constraint. And so what we do with Lagrange multipliers, extrema are where two things happen. One, grad f equals lambda grad g, and 2, g of a1 through an equals 0. All right, so the gradient of f, you could calculate it all very carefully. I'm going to get a 1 over n. I'll get this untouched except when I differentiate with respect to the variable. So remember, the gradient is first I take the derivative with respect to a1. So I'll just do one component very carefully. So I'm going to have the first component is df dA1 dot 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 dot. So I'm going to have a2 to an to the 1 over n. And now I have to take the derivative of a1 to the 1 over n. That's going to become 1 over n a1 to the 1 over n minus 1. And then you'll get a similar thing for the second component, where you'll have a1, a3, an to the 1 over n, 1 over n, a2. And so I can pull this all out, and I'll pull out the a1 to the 1 over n because it goes in so nicely with that, and I get a1 times an to the 1 over n divided by n times 1 over a1, 1 over a2, dot, 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 1 over an. So that's going to be the gradient of f. All right. Any questions as to how we calculate the gradient of f? Again, it's a lot of algebra trying to think what is the best way to write the expression. And notice that I can pull out this a1 to an because it's going to be the same for everything. All right, so now I take the gradient of g. The gradient of g, fortunately, is much easier to calculate. And so when I calculate the gradient of g, what do I get? What's the gradient of g? 1 over n, 1 over n, 1 over n, 1 over n. Very nice. So if the gradient of f is lambda gradient of g, I get blanc, or blah, times 1 over a1, 1 over an equals lambda, and I can pull out the n, all ones. What's the only way I can have equality? All the ai's equal. Must have all ai's equal. So do we have a maximum or a minimum? What do you think, maximum or minimum? So almost surely apocryphal story. I apologize for those of you who heard this a few minutes ago in 317, but there's the story about the people who were trying to build the stealth bomber, stealth fighter. They were trying to maximize stealthiness. They set up a calculus problem for something that they needed to maximize, and they forgot to check to see if they were at a maximum or minimum. And they were actually at a minimum, and they built the show me plane. Okay, almost surely this is a false apocryphal story, but it is a great warning about the need to check and see, are we at a maximum or minimum? Well, we can do some tests. We want to choose values of a1 through an where it's easy to compare the arithmetic mean and the geometric mean. And if I choose the values 1, 1, 1, 1, 2 to the n, so I have this n minus 1 times, what is the geometric mean? It's 1 times 1 times 1 times 2 to the n to the 1 over n. What's the geometric mean? 2. And the arithmetic mean is 1 plus 1 plus 1 plus 2 to the n over n. And what can you say about that? Got to be a little careful. So is it greater than 2? It is definitely greater than 2 if n is big. You know, if n is 3, sure, we've got 8 over 3. What if n equals 2? Yeah, we're still okay. We have 2 squared over 2, and we still have this extra 1 over here. If n equals 1, actually it's an equality. Well, the arithmetic mean and the geometric mean are an equality when n equals 1. Okay? So this is a great way to finish the proof, is we know it's got to be a maximum or minimum from Calc 3. Is it a maximum or is it a minimum? We can figure this out by looking at special points. The other thing we could do is we could take the limit. We could send one of the a's down to 0 again. And if we send one of the a's down to 0, we will see the geometric mean is going to 0 and the arithmetic mean is really not changing that much. All right, so this is a good place to end. Any questions on the multivariable calculus proof? So again, this is another great technique. This is another application of Lagrange multipliers. So if you haven't seen applications of Lagrange multipliers, here's at least one of them. Okay, so what I'm going to do now, I think